Okay. So, finite state machines are in this chapter called discrete systems, and I'm going to add some more stuff into this discrete systems chapter, but this is the only lecture that I've gotten together so far. And just the chapter in general is talking about systems that have well-defined states at certain points in time, and so a lot of computer. There are actually analog computers, but most computers today are digital, and they have these different distinct states that are governed by the state of the memory, the state of the inputs and the outputs, and there are a lot of aspects that come into that. For instance, there are no continuous signals. There are only digital signals that are sampled at certain values of time. So we're going to eventually talk about sampling, A to D conversion, which is sampling, and then D to A conversion, which is to convert a digital to an analog signal. We'll talk about all of these types of considerations, including just sampling, like sampling theorems, like how fast you need to sample to represent a signal, that type of thing. So we'll talk about all these things. But for now, we have a very specific topic, which is not really, I don't want you to get the impression that discrete systems are all about finite state machines. They're not. This is sort of a way of framing how to do control in digital systems. So it's useful because it scales pretty well without getting too conceptually dendritic, I guess is one way to call it. Like you can keep things straight even when you get to really large, complicated systems. So that's why these finite state machines are really useful for doing control, and especially for a lot of industrial processes. There are lots of times you have like a bunch of different sensors that you're monitoring. Like, is this, for instance, is this platform at level 1 or level 2? And is this sensor detecting that, for instance, fluids flowing down the pipe? And then like all of these possible situations that can occur. What should the control system do? How should it act on the system? So finite state machines are really nice for that, and so it's a very practical way to go through. And you say like, okay, like I know like if this happens, I want this to happen, but like how do you bring that all into a real-time operating program that's like taking these sensor values and acting on the system appropriately, and how when that system gets really complicated, how do you scale it to that without having just some mess of code that when you have a bug you can't find out where it is or why it's doing what it's doing. So once we get beyond really simple systems, it's really difficult for us to conceptualize what the control system should look like. So these can be really helpful for that. So question?
What does it mean, state here?
So we'll talk about state. So state is one of the definitions we'll start with. So a program that sequences a series of actions or handles inputs differently depending on what mode it's in is often implemented as a finite state machine. So here we mean that a state is a condition that defines a prescribed relationship between inputs and outputs, and between inputs and subsequent states. We mean something, it's analogous to what we mean when we say, like, what is the state of the union, or what are the state of affairs, right?
The government is shutting down like this.
Yeah, right. Hopefully our system states are better than the state of the union. But we have a certain way that things are, and we're specifically concerned not just with, because if you think about, how things are in a system, you could get it to a very detailed level, right? Like, well, I mean, and it's this temperature here, and it's a totally different temperature over here. So like the state is like there's an infinite amount of information in there, right? It's totally continuous. So and the geometrical relationships of everything, that all describes in the broad sense what the state is of the system. But we narrow that down with this definition by saying that is a condition that defines a prescribed relationship between inputs and outputs, and between inputs and subsequent states. So what we're saying is, okay, we're going to really just boil this down to the things that affect the outputs that we care about to a significant amount. So we're going to ignore small effects, small differences in the state of the system. And we're going to just say our state is those aspects of the system that affect the output. And that given some input, these states have some way of describing how those inputs become outputs. So if you're familiar with state space modeling, which I know a few of you are, the state model concept of inputs, states internal to the system, and then outputs that go from the system. It's very much if not analogous, if not identical, analogous to that same concept of state. So that's what we mean by state. A finite state machine is an algorithm that can be in a finite number of different states. So what we're saying is we can describe in a finite number of ways the different states that can exist in the system. So clearly, we're ignoring any continuous possibility, right? There's any continuous variable that sneaks in there makes it an infinite state machine, because any continuous variable can have an infinite number of states. So we always are going to have discrete variables that can only take on a certain number of states. And often we don't have, each variable can't take on a million different states. Possibly a million different values. Typically, we limited it to like low, high, or some small number of variable values. But I mean, technically, you can go to any number of finite number of states. For example, consider the control algorithm for an elevator operating between two floors. The elevator has 4 possible states. So it could be stopped on floor 1, could be stopped on floor 2, or it could be moving up, or it could be moving down. So those are the 4 possibilities. Clearly, we aren't saying anything about like the velocity or whatever. So for the things we care about, which are, our outputs, we care about certain aspects of the system at a really high level. So we don't care about like specific what is the velocity of this at a given time. For this example, we might in reality care about that. But for this example, we're saying that's irrelevant to us. We just want to know if it's stopped on floor 1, stopped on floor 2, it's moving up or it's moving down. That's what we care about. Maybe the level of the control algorithm is just operating on that level. It's not concerned about anything else. Inputs include the buttons that are pushed in the elevator car, so the user hitting those buttons, and on each floor, so the user inside the elevator and then the user in the hall waiting for the elevator, and limit switches indicating that the car has reached each floor. So these would be the different inputs that we would have. So at a given moment, we've got access to what's going on with the buttons and what's going on with the limit switches. So those are our inputs. The outputs are the commands. So we are saying we're the control algorithm. We're taking the perspective of the control algorithm. The inputs are coming in. Given those inputs, given our current state, we're going up and this button is pressed. What do we do? So these are the outputs. This is what we're going to do. This is what the control algorithm does. First, the command would be to the lift motor. So like, for instance, raise me up. I want to be, maybe I'm stopped on floor 1, and an input is that somebody hit a button on floor 2 to get the lift, and so I'm saying, lift motor, take me to state 2. So first take me to state 3, and then I'm going to end up in state 2, which is stopped on floor 2. It's really interesting. Once you really break it down, like even a really simple problem, it's like, oh yeah, well, it needs to go up. But like, how do you tell a machine that? There's actually a little bit of detail there. So we also have the elevator doors. So for instance, if it's stopped on floor 1 or stopped on floor 2, we might want to tell the elevator doors to open if somebody pressed the button, or if somebody from the inside pressed the button and that's the destination that they wanted to be at. But when it's in states 3 or 4, moving up or moving down, we would never want to tell it to open the doors, right? It'd be bad. And sometimes these control systems have independent systems running simultaneously that are as independent as possible. So for instance, the elevator doors opening when the lift is moving, sometimes you want to have, if it's something very dangerous like that, sometimes you want to have an independent system that's monitoring that and choosing an override command based on something like that. Like for instance, if the lift is moving, never let those doors open. That reminds me of somebody I know who helped design the control system for the neutron therapy radiation machine at the UW. So it's like this crazy apparatus, like accelerate particles and smash into people's bodies. It's wild. But some of the early radiation machines actually, there were 2 issues that they had. One was sometimes it would be delivering radiation when there were treating people in the room and not just the patient who was trying to get the treatment. So people were being exposed to radiation when they weren't even supposed to be treated. And then sometimes people were being overdosed with radiation accidentally. Both are really horrible things, and like people died from it. Like people who shouldn't have died from these devices died from them. So like really horrible early accidents with them. They never had that at UW, fortunately, but they did have that other places. So when they developed the control systems, they have like hardware level controls over this. Like if the door is open to the room, there's a hardware independent system that will not let power flow to accelerate the particles. So like, no matter what, if there's like some crazy bug in the software or whatever with the control system, at the hardware level, there's a switch that's going to disconnect and like it won't flow. And so they have these sorts of controls in there in very safety crucial applications. So something to keep in mind. But yeah, I mean, this is like, these are kind of cool, right? These are like, you could imagine yourself being in charge of like designing this sort of a control system, right? And you have to figure out this state is occurring, these are my inputs, this is what I need to do. Good. And then also we might want to output indications in the cars and on the floors, like where the lift is. Yeah.
In the elevator.
Yeah, so maybe lights, maybe dings, you know. The outputs and the transition from one state to another depend on the current state and inputs. Okay, so what are we doing right now? Are we on floor 1? And also, what are the buttons doing? You know, what are the inputs? So a state machine for which outputs are functions of both the current state and the inputs is called a Mealy machine. So in this example, the elevators, and in a later example we'll do, and in the lab, we're going to have Mealy machines. It's just a subtype of finite state machines. A state machine for which the outputs are functions of only the current state is called a Moore machine. So if you're in this state, do the next state. If you're in this state, do this other state. So subtypes. An advantage of using state machines is that the necessary logic can be represented graphically in a state transition diagram. A state transition diagram shows the input-output relationships and the conditions for transitions between the states. A skeleton of code that implements any state transition diagram can be standardized. Okay. Let's examine the state transition diagram for a simple example and show how it might be coded. So that's what we'll do here. This is like the elevator example. Actually, it's a lot less complicated than the elevator example. It's a really simple example. And we're going to look at different ways of representing it, different graphical ways of representing it, and then a table way of representing it, and then a code way of representing it. And then this code can serve as a sort of template for any C-based finite state machine, which is pretty cool. So let's examine this system. So this system contains three states, A, B, and C. Its only input is the sequential count of a variable clock. So it could be 0, 1, 2, etc. Its outputs are a variable out and the clock, which the algorithm may reset to 0. So the clock is both an input and an output. So we are going to both have it come in and have it affect what we do, and also we're going to change it. The clock increments at a fixed rate. Potential state transitions are evaluated at each clock count. The state machine operates as follows. The system stays in A until the clock is 2. Then it sets the output variable out equal to 1 and changes to state B. It stays in state B until clock is 5, and then sets the out to 2 and changes the state to C. Finally, it stays in C until clock is equal to 9, and then it sets the out to 0 and resets the clock to 0, and changes the state to A. And then we're going to just keep doing that same thing over and over again, right, once we're back to A. So we've got this sort of loop that happens. The process repeats indefinitely, producing a periodic output of 9 clock counts. A plot of the output would look like that of figure 4.1. So if we were to look at the out variable, sort of plotted versus the clock here. So when the clock is, say we started here, clock is 0, 1, 2, and then we transition states from state A with out equals 0 to state B, which is out equal 1. And then we go along until the clock is 5, and then we transition from state B to state C, and then state C transitions back to state A when the clock is equal to 9, and we reset the clock from 9 back to 0, and we just continue on. So it's pretty straightforward how to conceptualize this example. Is just sort of change. And you see that the really key thing that's happening here that we're looking for from a control perspective is we're waiting for these state transition conditions, right? We're waiting until we see, oh, okay, clock is 2. That was our condition for a state transition, right? State went from A to state B. And then when we got to clock, we were watching the clock when it hits 5. We go from state B to state C. So those are the key moments. The other times, at each clock count in between, these intermediate ones, we don't do anything. We just wait. We wait until this condition happens. And so when you're in each state, there is a set of conditions with your state and your inputs that you're monitoring. And you're waiting for that transition to occur. And then when you're ready for that transition, you make it.
where is this diagram come from? Like the state level, the step function.
So what we're saying is we're just calling it the out variable. So we're setting out. So out is equal to 0, out is equal to 1, out is equal to 2. Now, when we actually implement this in hardware, like we'll do in the lab, we're going to be sending I/O, right? It's going to be, when this state happens, we're going to, for instance, print something to the LCD. We're going to set the motor speed to such and such via changing some pin, right?
So this diagram is just to, for example, what are the inputs in a certain state of clock?
That's right. So it's one way to visualize what's going on. It's not. It doesn't scale very well because once you start to get more and more stuff, it's hard to follow a diagram like this. But for simple systems, and we'll do something like this for the lab that shows some of the information, but not even all of it, because it's just too much to show in one diagram. And yeah, so the clock increments at a fixed rate. Potential state transitions are evaluated at each clock count. So that's kind of important for timing. So timing is a really big part of this embedded computing endeavor, right? Is trying to control time. So yeah, like we set this state to something, but we want that to be not just something that happens at some point. Like we want it to happen precisely at a predictable time. So that's one of the aspects of this lab that we'll be doing, lab 4, that is most difficult, is controlling time. So we'll see. I'll give you strategies. I'm not just going to let you guys just try to figure it out. Okay, I'm sure you would do fine. Just don't want to give you guys more work. Okay, so that's how the state machine. So the state machine operates as follows. The system stays in A until this. I told you guys that, right? Yeah. Yeah. Okay. Good. So this complicated natural language specification, which was this last paragraph where I say, okay, when clock is 2, set the output to 1, etc. And even that diagram can be represented more simply in a state transition diagram, such as that is 4-2. So this diagram, I think, is a little easier to understand. You look at it and you say, okay, state A. You're in state A until the clock is 2. Then you change the output to 1, and then you're in state, and then you change the state to B. You're in B until this condition is met. Clock is 5. Then you output 2 and you change it to state C. And then you're in state C until the clock is 9. You set the clock to 0, you set the output to 0, and you change to state A. So this is called a state transition diagram. And it's useful for representing finite state machines. Each state is represented by a node in the graph, and then you draw arrows for transitions. So pretty useful, and we'll do that for the lab as well. So this is the notation that we use for the arrows. So the event that caused the transition, and then you do slash outputs as a result of the transition. So that's the so like we did here, we said when the clock is 5, this is the condition, then we output 2. And then this is the transition from B to C. So C is the next state. Often the information in the state transition diagram is described in the form of another representation called the state transition table, such as that of, oh, I put in the wrong, this is the wrong reference. Table 4.1. Wow. This is I believe this is the table that's in the lab or something. I think it's the one in the lab. Yeah. I don't know why. Put in the wrong one. Okay, so table 4.1. So let's look at table 4.1. So we can represent this in a table form. And I like this way of putting the table, although this is often labeled current state, input, output, and then next state. That's kind of like the typical way of labeling these. I kind of like being a little bit more descriptive in the labels. So when the state is A, B, C, and the input is, and then you look at the input, so clock is 2, clock is 5, clock is 9, then output these things and make the state one of these things. So that's how we'll also build a table for the lab as well. So when state is A and the clock is 2, then output 1, and you don't have to do anything to the clock. So this O means, this circle means no change. So don't change the clock. Leave the clock as it is. So we could say, I mean, in the table, of course, the clock is something. And sometimes we can describe that in the table, and that would be useful. But it's inefficient to, of course, redefine it. Like, we're going to use this table to write an algorithm. We wouldn't want to state something that we don't need to change. We don't want to change something that we don't need to change. So in this instance, we don't have to change the clock. So we're just going to leave it out. We'll say don't change the clock. We're only going to put things in there that we have to change when we do that state transition. So out is 1. We don't have to change the clock. And then we make the next state B. So we change the state from A to B. B goes to C when the input is 5, and the output then you specify as 2. Don't change the clock. C is the state until the clock is 9, and then you set the output to 0, and you set the clock to 0, and you just go back to A.
In this unchanged, it means we count the clock 2 until 5. I mean, from A to B, we don't change the clock. Like state
Correct. Right. In A and B, we don't.
One upon another, we don't change it.
That's right. The clock gets incremented on every step, but we don't change the clock inside the state transition. So we typically will put the clock outside, in the main function, and we'll do timing outside of these states, and that's just so that we don't have all of our state timing is controlled by one central clock, and we don't have the possibility that there will be different clocks going on in different states, because we implement these states as functions, and so inside that function, if you have your timing inside each function separately, then you could mess with the overall timing by just changing one of them. Whereas if you put the timing loop in the main, then you have one master clock. If you change that master clock, changes the rate of the whole thing. So that's generally a better idea than putting clocks inside of each function. Although in certain cases you might do that, you just have to be careful with it. It can be dangerous. Okay, so as shown, the table lists all possible transitions between states, the conditions that cause the state transitions, and the corresponding outputs. Now, how can this be efficiently coded? The listing on the following page illustrates one possibility, and I also give you a reference to a paper that was written that I think it was like 2004 or something, 2000, that describes this sort of general structure of a C program for state transition programming. It's pretty finite state machine programming. Pretty nice paper, pretty readable. So you will need to study this code carefully. So we're going to look at this code in a minute. be sure that you understand all of the C constructs. Some of them are tricky. So I'm gonna. This is just sort of a description of the code listing. So I'm just gonna walk us through the code listing and talk about it. We won't go through that explicitly. Something to note for the grad students who are looking for research topics for this lab that we're coming to, lab 4. Finite state machines are a topic that you can probably find relatively recent literature on. Like, it doesn't have to be like, I mean, if it's in the last 20 years, it's fine. Like, you can use anything. I mean, even older stuff, if it's relevant, you can use. I'm not putting a date on it, but there's good stuff out there on finite state machine. There's good papers and stuff, so you can find that. So that would be a good topic. There's a lot of different things you could do at your stuff on, but I think finite state machines would be an interesting one. You probably find some cool literature on it. So, and you might start with this Gomez paper because that has references. So you might find that's how we find a lot of papers. Is we start with one, and then we look at the references that they cite, and then we find the other ones. Sometimes Wikipedia is good for that too, because you can start with Wikipedia and be like, all right, here are a couple of sources, so then you look there, and then it helps you. I am not somebody who doesn't like Wikipedia. I know some professors don't like it. I love Wikipedia. It's my favorite. Well, I like it a lot.
Because I think it is somehow confusing. Too many people can post on the same topic.
Yeah.
If you are not knowledgeable about a topic, you can get confused easily because
Totally.
one author say that, the other author say that. Anybody can post.
Not all of the articles are good, but a lot are really good. So, and not always written in a way that's super easy to read, but sometimes they are. It really just depends on the article. You have to be discriminating, as with everything on the internet, especially nowadays. Hashtag Russia. Okay. So, let's look at this. Let's look at this code. State machine example. So, here's some prototypes. We're gonna have some functions here: state A, state B, and state C, and another function initialize. So we have a function that represents each of these states. So A, B, and C. And so we're going to be making a call to this state function when we're in that state. And each clock cycle will make a call to that state as long as we're in it, to that function representing that state, as long as we're in that state. When we transition to another state, we'll, at every clock cycle that we're in that, we'll call that state function, etc. So we're not actually, notice, void for arguments and void for return. We're not returning anything from these. We're completely working with global variables, right? Static is how we're gonna implement it. Is static variables that everyone accesses the same globally. And then weight is another function that we'll use. Which I actually don't, did I put weight in here? I don't think I put weight in here, which is fine. Weight is the same, it's meant to be the same weight that we are using in the lab. So we'll talk more about weight.
In the previous note for that one, you have weight inside.
Ah, really?
Yeah.
Okay. Yeah, I'll have to get, well, because weight is in the lab, the last lab. And it's in this lab, so we'll be using weight.
And it's a pretty easy function.
It's not so bad. Pretty much
But
just
how
like
many
going through a loop.
Yeah.
It's like 3 lines. I think you
Yeah.
can make it all.
How are we counting times in the machine?
And that we'll talk about that when we talk about lab 4. So you guys are actually going to calculate how long the weight function should take. Count using the number of clock cycles that it should take, processor cycles it should take to do each each instruction on the processor.
But how do we know that? How do we know how many clocks it takes?
We'll talk about that. It's described in a specific manual that I give you guys a link to. So, yeah. It's not. Yeah, it's pretty much like an exercise of looking up you have to do some interpretation though in the manual because there's a lot of variant for each instruction.
Also, isn't it like I know in like PCs, it's they don't do everything like in order necessarily. They try to do the most efficient thing, so they try to do a bunch of things at a time.
Yeah.
It, like all kind of shares the like clock queue.
Yeah. So we are. You're right. So part of the struggle with working with modern processors is that they're trying to make them more and more efficient, and they're doing a lot of queuing of instructions in ways that are out of order or parallel, and so timing it gets harder and harder with them. The way that we've set this up, it's not that ARM does not do that, but the way that we're using ARM with C, we have control over that. So in our wait function, we can predict for this processor how long this should take. If you ran that same function on another processor, it might not be deterministic in another system. So if you have specifically an ARM system and you use just the commands that we're going to use in C, and you implemented it in this way, it's deterministic. But you can get yourself into trouble if you try to do timing on just any old system and on like a PC system. No fun. I mean, because you could have a different process that's going on, totally unrelated to the process the thread that you're working on, and you don't have any control of when those instructions get executed. So, yeah, this doesn't apply in general, and even Linux was not originally meant to be a real-time embedded computing operating system, but it's been over the years sort of hacked into shape that allows you to do the timing. There's like so many layers, including the operating system. And so for us, for the operating system that is on the MyRio, which is a Linux-based operating system, it's made for real time, and this ARM instruction set in that environment is deterministic. But that is not something that's just a given in general. So that's part of why these systems, like these embedded systems, they're designed specifically for people who care about timing. Like, because, I mean, it's not as efficient if the operating system doesn't have total control over which goes where. But that's okay. We're willing to sacrifice that because we need to be predictable with our time. So we need to know what real time is. That's why we call it real-time operating system, real-time control, because we need to know what the real time is of each instruction that's being run. So, yeah. Good. Okay, so we're going to use typedef and then enum. So state A, we want to define these three symbols, state A, state B, and state C. And we want state type to be a variable that can take on state A, state B, or state C as values. Okay? And then this is like the tricky statement. So define an array of pointers to each state function. And what we're doing here is, it doesn't really make a lot of sense when you look at it this way. But the whole motivation is that we want to be able to call function state A, function state B, and function state C in a loop. And so we're going to use this really awkward construction of an array of pointers to each state function. So we have to explicitly use the name of the function, state A, that we use to define our prototype for state A. And then we'll use to define the state A function. It's an awkward construction, but it is a little bit nicer than some other options that we would have to explicitly write out if statements, and it's a little bit cleaner to write down this way. So this is like it's a bit of a hack. It's not like a standard way of doing things. Usually you're not going to come up with an array of pointers to function names, but this application is one that is like really nice to do that. I've had to do this in a couple other programming languages, and in every programming language I've encountered, it is a hack. They don't give you usually very good control over this sort of thing. It's sort of like a meta process on what you're usually doing. Because, like for instance, in MATLAB, I think you have to use some weird combination of the exec function to like take a string and then process it as a symbol. It's weird. I'm reaching back a few years, but this is like, I remember when I had to do this, and I thought this is just such a, it's like there's got to be a better way. But it turned out that was like the only way to do it. So there's always some sort of hack when you want to loop through something in terms of variable names. So even with more abstraction, like in MATLAB, it's still bad. So. And then we define global variables. By defining them out here, we don't explicitly say extern, but when you define anything outside of your main, then it is implicitly so. So we make them static, externs, global variables. The current state is here being defined as a static. State type means that it's going to be either state A, state B, or state C, right? It's this enum type. And we're going to call it current state. So when we set current state, we have to set it to either state A, state B, or state C. We don't have any other options because it's of type, state type, which we defined to be an enum. Okay. And then clock and then out are two static ints that are global. And then inside of our main, we first initialize the state machine. So let's look at that function. It sets current state to state A. It sets the output to 0. And it sets the clock to 1. So we are starting out at, state A. I guess in this, we start out in state A, and then when we're in state A, we're waiting for the clock to be equal to 2. So if I look at the state A function, so I initialize, and then we'll go back to the main. So while 1 means forever, right? Keep doing this. While 1 always evaluates to true. So state table of current state is called, which is to say, call the current state function. So cur state was set and initialized to state A. So it's going to call the state A function. So we call state A function. Let's look at state A function. It is going to say if clock is equal to 2, we're going to do something. But otherwise, it's just going to return, right? So it's going to, so say the first time through when clock is equal to 0, it's just going to return. So when it returns, then inside my main while loop, we go to the wait function. So we're going to wait some fixed time interval, and then we're going to increment the clock to 1, and we're going to call our function again. And still the clock is going to be 1 and not 2, so we're going to just return again, and then we're going to call it again, and then it's going to actually be clocks 2. And then we can finally do something in state A, which is to change the current state to state B, and then set the output to 1. And then when we return, we'll be in state B, so it'll call, instead of calling state A function, it'll call state B function. And then we go down to state B function, and it's going to keep calling that one until the clock gets to 5, at which point it will say, okay, we'll set the current state to state C, we'll output 2, and we'll return. And then we go to state C function, we'll go around until the clock gets to 9, and then we'll set the clock to 0, set the current state to B, set the output to 1. Don't run this, by the way. It'll just run forever. Oh! Good catch, Dane. Typo. State A.
If we set state B, it will get confused, right?
If we went to state B, then it would just go back and forth between B and C, yeah.
But the clock will be 0 at B, so it will mess the program up.
It wouldn't, because it would just keep incrementing up till 5. So it would be 0, 1, 2, 3, 4, 5.
Last longer because we use the state B instead of A inside the.
Exactly. So it would look, instead of like this graph,
All are B.
it would just be like this and like that. Then what I drew is the first time through it would look like that, and then afterwards it would look like that. Oh man. Whew. This morning I thought I screwed up in this algebra thing in systems, but I actually hadn't. But I was convinced for a minute that I did. Whew. Okay, so state B should be state A. Okay, any questions on finite state machines? What?
Out should be 0 too, right?
Yeah. I like totally, what it was I was copying and pasting, and I was like, oh, I can just change things. And I didn't change it. This is what always happens. I don't change all of the things I needed to change. This should be 2. Or no, it should be 0. Because when you're in, I mean, it's kind of weird, but the previous state function is the one that sets the next state. And then so output being 0 is because the next state is state A, which should be with output 0 the whole time. So.
But in this case, we don't put like the stop function for that one. Right?
So we didn't put it in, and this is not something that you would actually want to run because there's no way to get out of this, right?
Yeah.
I mean, you would do this if you were, you have no exit, so there's always some way, like, it's not like once we set up an infinite loop in a computer, we can never get out and then you just throw that computer away. You can just, unpower it or whatever it is, and it'll stop the cycle. But unless, of course, you built yourself a firmware-based infinite loop that always rebooted it whenever you powered it back up. So, yeah, there's always a way out, but we did not give it a programmatic way out. It does not have a way to exit this. Although in our lab, we'll have a way to exit the loop.
Like if you press the stop button.
Yeah, exactly. This is going to be a stop button. So that's going to be a state that we're going to look for that input. We're going to look for that button to be pressed, and once that button's pressed, then we'll exit.
It's because I remember the first development of this PDA, the operating system on PDA by Microsoft.
Hmm.
When you rebooted, everything just new. So all your file lost if you lost power.
Oh, whoa.
Yeah.
That's bad.
Yeah. So
That sounds like an exercise in frustration. This time I won't let it power down.
yes, oh, it's 1%. Where is the plug?
You're like shoving old ladies to get to the plug.